Good morning, everybody. Happy Monday. Good to see you again. Well, I don't get to see you, but you get to see me, I guess. We're going to talk today about Newton's laws of motion. Now, this should be a little bit of review. I believe you've talked about this when you were in elementary school, fifth or sixth grade. Now, here are the laws. And by the way, I'm going to put up a PowerPoint that has these laws that you can get written down in your notes so that you have them for a quiz that we may do later on. You can count on a quiz. So the first law of motion, these are Newton's laws of motion. Newton was a scientist he's the guy that you know who the story goes that an apple fell on his head. And he said, oh, gravity. And he came up with some laws of gravity. He also came up with laws of motion. Okay, the first law, and you guys are familiar with these, right? Says an object in motion will stay in motion, and an object at rest will do what? It will stay at rest unless there's some force to act on it, unless there's something to make it change its motion. If you remember when we talked about balanced and unbalanced forces, we said that an object will continue moving at the same speed, or it will continue to sit where it is unless the forces are unbalanced. As soon as the forces are unbalanced, then it will speed up, it will slow down, or it will turn, right? But if the forces are balanced, it will keep its motion or stay at rest. This is often known as the law of inertia. Inertia is just this idea that an object wants to keep doing what it's doing. And the more mass an object has, the more it wants to keep doing what it's doing, and the harder it is to get it to change, right? It's much harder to get a boulder to move, to get it to change its motion, than it is to get a ping pong ball to move, right? You can just toss that thing. It doesn't take much force. So that's the first law. Objects in motion stay in motion, and objects at rest stay at rest unless there's something to make them change that. Something they hit or some force that stops them or speeds them up. Now, the second law says that a force, the amount of force on something is equal to its mass, how big and heavy it is, times how much it accelerates, how much it speeds up, slows down, or turns, right? So mass times acceleration is equal to the force. And the third law says, you guys know this one, for every action, there is a reaction that is both equal and opposite. Well, we're going to focus on law 1 and law 3 today. Let's ignore law 2 just for right now. We'll come back to that another day. You've seen this a little bit and you've done some problems, but I'll explain that more in depth later. So we're going to deal with law 1, objects in motion, and law 3, every action there's an equal and opposite reaction. And the best way that I can think of to discuss this, I'm actually going to turn off the lights here in the front because I think there's a glare. Let's see how that is. Is that better? Maybe that makes it too hard to see. I think that's a little better. So the best way for me to think about this is to go out into space, because in space there's no friction. There's nothing to stop things from moving, right? So let's go ahead and go up into space. We're going to put our spaceman up here. Let's see how I can do on drawing my spaceman. There's his little space helmet. His eyes sticking out there. Okay. Get to see my art skills today, which are not particularly impressive. Here's our space guy. Got to give him a little American flag there because we're patriotic. He's got a little air tank on there. All right. So space guy is floating up in space, right? And while he's up there, he takes a baseball and he throws that baseball. Okay, he's got an object here and he throws it. So it's now moving this direction. Well, what is going to happen to that baseball after it leaves his hand. Before it leaves his hand, we know that he has it. He goes like this, and he speeds it up, speeds it up, speeds it up, and then he lets go. So while it's in his hand, he's applying a force, and it accelerates, right? It speeds up. Now, as soon as it leaves his hand and continues going this direction, what does it do? Does it speed up after that? Does it slow down? Does it keep the same speed? Well, it keeps the same speed, right? He has it here, goes faster, 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 leaves his hand, and at that point, there's no longer anything pushing on it. His hand is not applying a force anymore once it leaves his hand. And so it won't speed up anymore. Is there any friction in space? Not really. No. In all essence, there's not, right? There's practically zero friction. And now there's no forward force on it. There's no push on it. So the ball has no forward force, has no friction force, has no force up or down. So we would say the net force on the ball right now is 0 newtons, right? Because it's not in your hand. So there's no force there. And there's no friction. There's no gravity or anything out in the middle of space. We'll say we're away from planets. And so that ball has a net force of 0. Well, we know that if the net force is 0, if the forces are balanced, what does that mean? Does it mean the object has to be sitting still? We talked about this the other day. No, it could mean that. It just means that the object keeps doing whatever it was doing, which in this case, if it left his hand going 45 miles per hour, if that's the speed it got up to, and then it leaves his hand, and the net force is 0, it's going to keep doing that. It's going to continue in a straight line at 45 miles an hour forever. Unless what? Well, an object stays in motion unless acted on by an outside force. So at some point, it would probably go near a planet, maybe hit a rock in space or something, and then it would stop. If it hit something or if it got pulled by gravity, it would change its direction. But assuming you're out in the middle of space, it's not near anything, this would just keep going at 45 miles an hour for a long, long time because there's no forces acting on it. That's the first law. An object that is already in motion will stay in motion unless acted on by an outside force. That's the first law. Likewise, an object at rest stays at rest unless acted on by an outside force. And that's why it's hard to get something going. If you have a big rock here and you're trying to push it down a hill, right? It takes a lot of effort to get it going. Now, once it gets going, it goes pretty easy, right? After a while, gravity takes over. But getting it to change what it's doing is the difficult part. So, again, take that ball. While it's in your hand, the net force is not 0, right? While it's in your hand, you're applying a force this direction. And you get it faster, faster, faster. Leaves your hand. There's no more force here. There's no friction force. Net force is 0 at that point, and it will just continue in a straight line. Now, the third law. Let's talk about the third law here. The third law says that for every action, there is what? What did we just say? For every action, there is a reaction, something that happens because of what you did, that is equal and opposite. So let's get back to our spaceman here. You have this ball in your hand here, right? Holding that ball, and you throw it. Now, if I'm here on Earth and I throw a ball, I don't really move, right? Maybe I step forward, but if I just I'm standing here and just throw the ball, I pretty much just stay here. So you say, well, where's the reaction, right? Well, if you go in space where your feet aren't on the floor and you're not held by gravity and there's no friction, and you take that ball and you throw it that way, what happens to you? What happens to our spaceman here? Well, we know that there's a reaction that is both equal and opposite. So when he takes that ball and he throws it, the ball goes this way, we'll say at 45 miles per hour. What happens to the spaceman? He actually goes this way, much more slowly. We'll say he goes this way at 2 miles per hour. Not very fast, but if you're in space and there's no friction there, you do this. You when you pull the ball, you go sort of like this, then you throw and you go back like this. Because you are applying a force on the ball with your arm, but guess what? The ball is actually also applying a force on you. This is weird, right? You can sort of think of the same thing if you go ice skating. If you and a friend are ice skating and you're on your ice skates and you push away from each other, well, you both go, if you're both about the same size, you both go like this, equal and opposite reaction. Whereas if one of you is bigger and the other is smaller, the smaller person will probably go further and the bigger person not as much, right? Same thing here. You take that little baseball, it has a small mass, and you throw it. It applies a force on you, just like you apply the force on the ball. So the ball has a small mass, so it goes fast, and you go back slow. Because you're harder to move, because you have more inertia, you have more mass. And the ball is easy to move, because it's small, so it goes that way really quick. That's the third law. For every action, throwing the ball, there is an equal and opposite reaction. Well, how on earth are they equal? Let's go back to that second law now, finally, and we'll end with this. So we know that force equals a mass times an acceleration. So you have this ball. Let's just say the force that's applied here today is, we'll just say 10 newtons. That's what you are going to apply on the ball. Well, the third law says that for every action, there's an equal and opposite reaction. And so that means that the ball applies how much force on you? 10 newtons, right? It's equal and opposite. You apply 10 newtons on the ball also applies 10 newtons of force on you. Okay, well, if we know that force equals mass times acceleration, right? Let's say that the ball has a mass of, just keep it simple, this is not realistic, we'll say 0.5 kilograms. That's the mass times acceleration. Let's say we accelerate it by 20 meters per second squared. Well, our force then would be 10 newtons that direction, right? Which we just said. 20 times 0.5 is 10. Now that's because this mass is small and the acceleration is large, and so you get that force, right? Well, on you have a bigger mass. You can have a small acceleration. So we'll say that your mass is, let's see, how can I get 10 newtons here? We'll say you have a mass of 50 kilograms times, how do I get 10 out of that? 0.02 meters per second squared, something like that. And you get 10 newtons there. You might have to check my math, that might not be right. But the point is that you have a big mass, and so because the force is the same, right? Same amount of force this way as this way, it means that you have a big mass, so you get a small acceleration. Here you had a small mass, so you got a big acceleration. You sped it up a lot in that time it was in your hand. Either way, the force is the same. It just means that the ball, which is small, will go quickly that way, and you, who are big, will go slowly that way. So again, action, throw the ball. Reaction, you go back more slowly this way if you're floating in space. So, in review, First law of motion. When that ball is in your hand, it is accelerating faster, faster, faster. It leaves your hand. The first law says that an object in motion will now keep that same motion until acted on by a force. It will continue going that same speed forever and ever in a straight line until something pulls it or pushes it or hits something. Second law, force equals mass times acceleration, meaning if you have a small mass, a big acceleration, you get this force. If you have a big mass, a small acceleration, you can have the same force. And the third law, for every action, throwing the ball fast, there is an equal and opposite reaction, which is moving slow this way. That's our lesson for today. I'm putting up some notes in a PowerPoint up on Google Classroom. I just need you to make sure you get those written down in your notes so that when we do come back to school, if that happens, that you will have them available to you and so that you can use them on quizzes and things like that. So just write down the 3 laws that I have in the PowerPoint. That's all you have for today. No assignment to turn in, but please make sure you get that because you will want that moving forward. If you need to rewatch this video, feel free to do that to make sure you get these things. And if you have questions, please email me and I'll see if I can answer your questions. Thanks, guys.